So today we're going to do a review on the things we talked about, and also I will describe the exam in more detail in terms of the format and the coverage, and I encourage you to ask questions. We'll have the exam tomorrow. You can take a double-sided note, letter size sheet to help you to remember things. We will cover all the x86 instructions covered through today. And besides that, we will also have questions regarding the microprocessor and microcontroller in general, also the some assembly language programming basics. Those are the materials we covered in the first 2 lectures. So I also encourage you to go back and review those. So not only the instructions, but also the basic things related to microprocessor, process-based systems, assembly language programming basics.
I was checking the schedule and it said tomorrow there's an exam review. What does exam review
It's
mean?
today, so I don't do a review for tomorrow.
Yeah, it says preview and review. So I used to.
Review is once you finish the exam,
Oh, okay.
we'll talk about the questions, some of them, just to give you an idea how well you did in the exam. These are the things you can bring to the exam. 1-page double-sided sheet of notes. You can bring calculator. No computers, no cell phones, smartphones. Exam will be 60 minutes, so we'll start at 10 a.m. sharp. We'll cover all the lectures through today. About the format, I described the questions a little bit last lecture. So we'll have basically 2 major types of questions. We'll have multiple choices and then short answers.
Would kind of the examples that we've been going through with like a list of instructions and say would that be an example of like a short answer? Is that what kind of something you expect?
Yes. So for example, when we talk about the shift instructions, we give you a few instructions that you will need to execute them one by one on the paper. So you will be asked what will be the content in register AL, what will be the content in carry flag. So that's a very typical example of questions on exam. For multiple choice questions, I will have so-called type A and type B. Type A is the regular multiple choice questions. You choose 1 correct answer out of 4. So those 3 other choices are incorrect. Type B is a special tricky one where we will give you 4 options. There could be more than 1 correct answers. It could be 1 or 2 or 3 or 4 correct answers. You need to choose all of them to get the full points. You can choose some of the correct answers, then you get partial credit. If you choose incorrect answer, however, you will get 0. So do not guess. If you know that answer is definitely correct, choose that one. If you're not sure, don't choose that one. And I was asked about the number of questions. My plan is to have 9 type A multiple choice questions and 3 type B multiple choice questions. And for type A, essentially we have 2 points each, so that's 18 points. And for type B, we have 4 points each, so that's 12 points. So total, we have 30 points out of 100 for multiple choice questions. And the rest 70 points will be on short answers. And I haven't decided how many questions I will have.
Do you do a bonus question or anything?
Not sure yet.
Is there a
Could be a programming question, if that's what you ask. So, could be a question. Say you want to write down 2 instructions to make sure after these 2 instructions are executed, you have that result in register AL or AH. So that's possible. I don't want to rule out that type of question. Yeah.
Are we gonna have similar question like the homework, or are they gonna be just different type of question?
So the questions from the homeworks will be the good examples that you will see on the exam.
The maps,
Yeah. So that's right. If we want to, let's say, test on the endiness of the data, we'll give you a memory map. We'll tell you, okay, starting from this address, I have this bytes in it. If I load a word, and what will be the value of that word? Any other questions regarding the format, style? No? Okay. So we talked about processor components, microprocessors for computation, input and output, and storage. So those are the basic components in a computer system. And also, I was asked about whether we'll have questions like explain this or describe that. It's possible. This class, the nature of this class is that there are a lot of things you need to remember. Not only you need to know how to apply these instructions, there are concepts that you need to remember, understand, and be able to describe. Instruction set architecture defines how programmers interface with hardware. Different processors will have different instruction set. Intel's instructions are different from ARM's instructions. So at assembly language level, they are incompatible. At high level language, you can have the same C program executed, compiled, and on different processors. But at assembly language level, you cannot take one assembly language program and run it on another processor. We have instructions, and their operations generally fall into one of these 4 groups: data transfer, arithmetic, logical, including AND OR, exclusive OR, and shift. And then program control. Operands. Operands are the data being operated on. Many of the instructions, many of the operations need data to work on. There are instructions that without any operands, but those are very few. For operands, for the data, we will need to figure out how are the bits interpreted. Whether these bits representing an integer or a floating point number, or a signed number or unsigned number. So we have to agree upon things in order for the microprocessor to know how to deal with these numbers. Given the example, the multiplication example, right? We know for MUL, that's for unsigned numbers. For IMUL, that's for signed numbers. So that's kind of the agreement between the microprocessor and the programmers on how a number should be interpreted. Also, we need to know the size of the numbers, the data, whether it's a byte or word or double word. And we need to know how do we reference the operands, or where these operands are stored. Instruction formats, how the instructions are encoded. When we write assembly language programs, we use dynamic, or the symbol for these different operations: add, increment, subtraction, move, and then followed by a 0, 1, or 2 operands. This is one instruction, and before the instruction, we can have a label to represent the address of this instruction. After the instruction, we can have a comment to explain what's the purpose of this instruction. For data storage, we have two options. We can store data either in a register or in a memory location. And these two different storage types have advantages and disadvantages. Registers are small, but the access speed is fast because they are on chip. They are part of the microprocessor. Registers are referred or referenced by name. So when you want to work on the values stored in a register, you just need to put the name of the register into the instruction. On the other hand, memory has larger capacity, but the access speed is much slower compared to accessing a register. Because memory is outside the chip. When we want to access data that is stored in memory, we need to go off the chip, go over the memory bus, which we will talk about in later of this class. And that causes some kind of performance penalty. So you have to wait a longer time for the data to come back from the memory. Memory often has hierarchies, but for programmer, especially for assembly language programmer, we reference the memory using address. Every byte location in memory has an address. That is to say, the minimal addressable unit of a memory is a byte. You can access a byte starting from address A. You can also address a word starting from address A, or even double word from address A. So depending on the data size, you or the microprocessor will read or write a number of bytes starting from address A. For memory, we will need to consider whether the address, because of the address, the data is aligned or misaligned. The simple way to figure out whether the data is aligned or misaligned is to figure out by looking at the 4-byte boundaries. So 0, 4, 8, C, nav. So that's the word boundary that we can draw on memory map. And if a word or double word is within these boundaries, then that's a line word or double word. If a word or double word sits across one of the boundary lines, then that's a misaligned word or double word. And the reason we use these 4-byte boundary is because of the memory bus size. The data bus for the 386 is 32-bit. That means at the time, the microprocessor can load maximum 4 bytes into the microprocessor or write 4 bytes into the memory. So that's why we have this 4-byte boundary. Anything across that boundary, you have to spend 2 accesses. That cause performance penalty. The other thing about memory is the endianness. x86 data is little endian. Little endian refers to we're gonna store the most significant byte at higher address and store the least significant byte at lower address. Again, we're talking about multi-byte data. For single byte data, there's no issue with the endian because that's just 1 byte. But with multiple byte, when the microprocessor reads the data from memory, it has to figure out how it should put those bytes into word registers to represent the correct data. Different processors may use different endianness. For x86, it uses little endian. Some specifics for x86 memory organization. In Intel x86 microprocessor, it has 6 segment registers: CS, SS, DS, ES, FS, GS. CS stands for code segment, SS stands for data segment. Stack segment. DS stands for data segment. And we have 3 extra data segments.
What is DS?
Extra. I don't know the representation of FSGS, but those 3 are all extra data segments. Each segment has 64 kilobytes. 64K, it's an interesting word, interesting number, because that is 2 to the power of 16. And that is the reason for effective address within a segment, we have 16-bit effective address. With a 16-bit number, you can find 2 to the power of 16 locations. And that is exactly 64K. Okay, so there's some connections here. Each segment has 64 kilobytes, and all the segments starts on 16-byte boundary. That is to say, the lowest hexadecimal digit of a 20-bit address is a 0. And that's the effect when we shift the segment base to the left for 4 binary bits. Logical address refers to this pair of values, SBA and EA. SBA is the segment-based address, and EA is the effective address. We have these examples here, DS, SI. So in this case, SBA is the value in DS, and EA is the value in SI. Linear address. Linear address is the actual address used within architected memory. In real mode, you can simply remember that this linear address is the physical address that is needed for the microprocessor to access memory chip or chips. And the way we get this linear address is by a 2-step calculation. First step is to shift the segment base register to the left by 4 bits. And the second step is to add the 16-bit effective address. So you do shift, then add. And the final result is a 20-bit address, and that is the linear address. To calculate the effective address, we may have different ways. That depends on the addressing mode used by the instruction. The simplest way is the direct addressing, where you have a pair of brackets, and within the brackets, you have an immediate value or constant number. That's called direct addressing mode, and the effective address is the immediate value. Yeah.
Always 16.
Correct. Effective address is always 16-bit, because think of
Calculation goes over that.
correct. Yeah. And simply because effective address is only used to find out the data within a segment, and the segment is 64K bytes. Only need 16-bit to address all the different locations. Other ways to calculate the effective address, for example, if you use register indirect mode, that's in the case when you have a pair of brackets, and in the pair of brackets you have a register. So the effective address is the value in that register.
So when it's in a bracket, effective address, you need to add the effective address, and then to look for the physical address, you need to add the segment-based address with the effective address.
Correct. So logical address has 2 pieces, SBA and EA. That's the 2 numbers separated by the column. And if you want to have linear address, you need to do the shift and then addition. If you already know the effective address, for example, if it is a number, then you're all set. Otherwise, you're gonna calculate the effective address by using maybe registers, two registers, or register with a constant number. So you do these additions, and depending on the addressing mode, you will use different elements to calculate this effective address. You could use base register plus index, that's called base index, or relative register relative, or you have everything together. You have base register, index register, and a constant. Or you may do the scaled index. Any other questions? We have registers, 8-bit, 16-bit, or 32-bit, and from the name we can tell what's the size of the data in a register. For memory operands, the data size usually matches the register used in the same instruction. Otherwise, we have to specify how many number of bytes we need to access from memory. We can use byte pointer, word pointer, or dword pointer. Then we move on to talk about different instructions. We started with the data transfer instruction, move. We can use move instruction with registers, memory, or immediates. Immediates, in our context, in our course, we refer to constant numbers. If we want to copy values to a segment register as a destination, the source must be a register. Oftentimes we use AX to do the data transfer. Move XX and move ZX are two extensions to simple plain move instruction. One is the sign extension, one is the zero extension. In this case, we're gonna copy the value from a register to another register, or from a memory location to another register by extending the upper bits. In this case, destination register has more bits than the source, and typically it's twice of the number of bits than the source. So on the upper half, we need to do extension. For sign extension, we just look at the sign bit of the original value and repeat the sign bit on the upper half of the register. If it's 0, then we're just putting zeros on the higher half. For exchange, that's straightforward, just exchange the content between the source and destination. Load effective address is to calculate the effective address and store that into the destination operand, typically a register. Load full pointer. Load full pointer is going to update to the destination and also the segment register. And we do that by loading multiple bytes from memory into these two registers. So let's look at sample. Let's assume that at this location, starting from this location, ds colon a to the r, we stored 5 bytes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 8. And I have instruction lds bx bracket ADDR. ADDR is assumed to be a symbol that represents a constant number, so this is the direct addressing mode. That is to say, the values we will use to fill out BX and DS come from memory. And the memory location is DS colon ADDR. That's the logical address. And I gave you, using this memory map, starting from this address, we have these bytes. So first thing we will do is to fill in the content of BX. And the size of BX is 2 bytes. So we need to load the first 2 bytes into BX. And I also should tell you this is the higher address. Just to make it clear that we are storing the byte sequence in ascending order on the address. So these 2 bytes should be put into BX. And BX is a word. When it takes 2 bytes, we need to apply the little endian principle. So BX will have 3, 4, 1, 2 hexadecimal. And after that, we need to fill out DS, because it's LDS. If you have LDS, then that's a different story. We need to get the next 2 bytes for DS register. So these 2 will go into segment based register. So DS will be 7, 8, 5, 6. When you answer questions, I encourage you to put these H suffix to numbers if you intend to use a hexadecimal number. Otherwise, it's assumed to be a decimal number. And that's 2 different values.
Whatever is loaded on the destination cannot be loaded on the secondary.
Well, if you are talking about the locations, that's right. If you load value to the destination register, then you're going to move on to the next 2 bytes and use those 2 bytes to load to the segment register.
Suppose the next one was BC and you loaded EBX, you would get the 7, 8 down to 1, 2, and then DS would be BC 9A.
Yeah, so you have this LDS EBX, then the whole first 4 bytes will be put into EBX. So that's going to be 7, 8. Yeah, DS will be.
If that was LES, then you would just simply change that DS to a DS.
Yeah.
Okay.
The name of the signal register doesn't affect. It doesn't matter if it's DS, DS, DS. It's always going to be the same process.
Yeah, so just those are just for different segment registers you update.
And if that was address plus 1, everything would be shifted up.
Address plus 1.
All
Yeah,
those
so
would
everything
shift
will be
up.
shipped up. You're going to start from here and take these 2 and then use the rest. We have flags in flag bit register. Here we list some of them: carry flag, auxiliary flag, sign flag, zero flag, carry flag, overflow flag. For these flags, since the generation of these flags depends on the actual computation, in some cases the possibilities or case to look at is very complex. So we don't really gonna give you questions regarding whether two numbers, if they multiply or something, how will they generate a flag. We will just test out some simpler cases. And we probably won't touch auxiliary flag or parity flag. Carry flag is the one we will use in the exams because carry flag is used in, for example, this addition instructions. And ADC is different from ADD. In that, you will consider the carry flag. Also, for later shift instructions, we'll know the carry flag will be updated. So that's why the carry flag is going to be a focus. Here we list these addition instructions and subtraction instructions. Addition, we have simple plain ADD, and add with carry, ADC, and then increment. For subtraction, we have subtraction, plain subtraction, and subtraction with borrow bit, and decrement, and negation. I'll skip this multiplication and division because we're not going to be testing that on the first exam. Logical instructions. And, or, XOR, not. So these logical instructions, they work on two operands. They do bitwise operation, and inclusive or exclusive or not. I think some of you may need to review exclusive or. What is the truth table? Exclusive or 0, exclusive or with 1. What is the value of it? If you don't remember, you want to go back and look at it. Go put it on your notes. That's fine. You do that. In the next set of instructions, the basic shift instructions, will move the value by a certain number of bits, adding zeros to the left or to the right. That's the basic shift. CF, carry flag, will hold the last bit shifted out, whether it's shifted from the left or from the right. CF holds the last bit shifted out. And we have two instructions, SHL and SHR. That's for shifting to different directions. The format is the same. First operand is the source, and second operand is the amount. But the source is actually used to store the result as well. So it's both source and destination. For arithmetic shift, especially arithmetic right shift, we will move the value to the right by a certain number of bits. And we will copy the sign bit to fill out the empty MSB. So you're going to repeat the sign bit on the top, on the empty MSB. The carry flag is again used to hold last bit shifted out. And the format is SAR, source, and comma, and the amount. The amount could be a constant number, could be a registered CL, for example.